The first concept we're going to discuss is that of statistical inference. As we've discussed prior in the course, we do two main types of statistics. We do descriptive statistics and inferential statistics, also called statistical inference. Big difference there is that with descriptive statistics, we're simply taking what information is present and reformatting it essentially. We may take a table full of numeric data and represent it as a pie chart. That would be an example of representing information we already have. Whereas statistical inference is all about looking at the information from a sample and using that sample information combined with some statistical techniques to make an estimate of the population from which the sample comes. So we'll start this chapter out by talking a little bit about sampling, look at a few different kinds of sampling, and learn how to get a valid statistical sample. First concept we're going to discuss is that of point estimate or point estimation. This is the act of using known statistics to estimate a single number for an unknown parameter. For example, if I take a sample, I compute the mean of that sample, I can then say that I estimate the population mean is estimated by that sample value. In the table at the bottom of our screen, we have several common measures that we'll be seeing a lot of. Notice that on the left we have sample statistics, so any characteristic from a sample is always called a statistic, whereas any of the same characteristics but from a population is called a population parameter. And let's go ahead and look at mean. We've worked with the population parameter mu, which corresponds to the population mean. The sample mean is going to be represented by x with a line over top of it. We call that x bar. Likewise, standard deviation, sigma, represents our population standard deviation, whereas lowercase s represents a sample standard deviation. And sample proportion, so in relation to experiments that are binomial, that have exactly two possible outcomes, we could say that a sample proportion of success is represented by p hat, and that could be used to estimate the population proportion of success indicated by the lowercase p. And finally, on this table I've added a count row. So if we see lowercase n, always think sample count. Uppercase N, always think population count. The next concept we're going to look at is what is random sampling. So first item on this page is random sample, and this indicates that lowercase n, think sample size, that number of elements are selected from a population such that every set of that many elements in the population has the same chance of being selected. Two possible ways to do this are sampling with replacement, in which case whenever an element is chosen it is returned to the population and thus could be randomly selected repeatedly, or more commonly sampling without replacement. In this case, this is where we do not place the chosen element back into the population. This would be the preferred method in order to have the best statistical sample possible. Random selection simply says that every element remaining in the population has the same chance of being chosen. And let's talk a little bit more about sampling. We're going to look at three categories or types of sampling here, the first of which is probability sampling. Random sampling, as we've just discussed, is one type of probability sampling. Any type of probability sampling is where the probability of each element being included is known, and by virtue of a sample being taken using probability sampling, this allows us to meet our requirements to be able to use that sample to make statistical inferences. On the other end of that continuum, we have convenience sampling, and here the sample elements are selected based on their ease or convenience to sample. For example, an internet poll is very convenient for the website offering it because it involves voluntary response samples in which a participant self-selects. Oftentimes this sort of sample would over-represent subjects that have a strong, usually a negative opinion on a subject, and we're not able to use a sample gain through convenience sampling to perform any statistical work or inference. In the center between those two is judgment sampling. In this case, perhaps for some reason we're not able to do probability sampling, so the next best alternative would then be to consult with a very knowledgeable person in that subject that we're surveying and have that person select the elements of the sample, potentially subject to that person's subjectivity, and therefore could be risky to use for statistical inference. Simple random sampling then is where we select, as discussed on the previous slide, our lowercase n number of elements randomly from the population. Let's look at a couple other techniques that can be used. Also, random sampling would be the stratified random sampling technique. Here, what we do is divide the population that we wish to sample into non-overlapping groups of groups or classes of objects that we feel have some similarity within the groups. Each of these groups are individually called strata, and each strata then has a component of the sample randomly selected from it. An example of strata might be to form 4 classes of freshman, sophomore, junior, and senior. Cluster sampling involves the clustering of elements into descending subpopulations. So for example, to take a sample of voters, perhaps I could access the county website to get the county-wide list of voters. From there, I could separate that into different clusters based on township membership. The townships could then be divided into precincts, and from those precincts I would draw the random elements that go into my sample. And finally, one classic method of random sampling is that of systematic sampling. In this case, we divide the population into the number of groups that we want to represent the final sample size, and from each of those groups we pick a random index position. So if I have 300 population size and I want to sample 30, what I can do is divide them into groups of 10, and I could pick the 8th person from each of those groups. And as an example of that, a teacher of a 100 student class may stand at the classroom entrance door, and every 3rd student arriving in the morning would be systematically sampled. With full attendance, this would result in a sample size of 33. And finally, for this video, let's talk about sampling and non-sampling errors. A sampling error is an inevitable consequence of the fact that we're going to use our sample and extrapolate or extend that sample statistic to estimate the corresponding population parameter. So if I have a population of size 300 with a sample size of 30, then the fact that the 270 population members that were not selected for the sample will have individually unknown values, then that leads us to expect that the actual value of that population, were it to be known, will differ somewhat from the sample value. And the formula is given here, simply says that our sampling error corresponds to the sample mean minus the population mean. This sampling error could be positive or negative. And statistically, the trend is that the larger a sample size is, the correspondingly smaller that an average sampling error will be. And the reason this is because with a small sample size, one extreme outlier value could make a big difference to the sample mean, whereas the higher the sample size, because of the normal characteristic of this distribution, the more samples, the more records we know that will be relatively close to the mean, that will tend to smooth out those rare outliers that appear. And finally, we also have a non-sampling error. This can be the result of many potential factors that are not related to the statistical computations, and examples of those would be ambiguous or leading survey questions, possible data input errors, perhaps a scale being used to measure sampled products is not working correctly, and so forth.